Hello, I hope you all had a good day and a great conference. My name is Lennart Schulenburg. I'm Managing Director of VisiConsult X-Ray Systems and Solutions, and we are a provider of high-end X-ray inspection, quality control solutions, and services. I'm sure you heard a lot about the possibilities of advanced manufacturing, especially additive manufacturing, focusing a lot on the chances, the positive aspects. Today I want to provide a word of caution. Additive manufacturing also has some challenges to get qualified to be used in field. And this is what we'll be talking about. And it will not be all cautious. It will also provide some insights on how you can achieve qualification and how you can move your parts into a production environment. So, as I said before, additive manufacturing is seen as the manufacturing technology of unlimited possibilities. Designing crazy bionic shapes, crazy light reductions, weight reductions, and stuff like this. But if you look into the reality, most additive showcases are small, minor parts. In the aerospace industry, it's stewardess brackets. In cars, it's clamps for doors or seat bracket holders, like small stuff. But is that really the big thing that we need for additive manufacturing to be successful? It's probably not. We see some showcases, like you can see on the left, this wheel suspension, or you see a brake, a braking saddle. This is a braking caliper. This is what's making a big difference. It's really a meaningful reduction in weight. It allows for customizations as we go. So this is the target that we have to achieve with additive manufacturing. But if we then perform a reality check, we look at what additive manufacturing is currently used, and we see its product development, its customized products, its flexibility, co-creation, tooling investment, demo products. But where is production? Somewhere in others, I would guess. Maybe a little bit in here. But what we can see is that additive manufacturing is not yet widely adopted for production. So that could be an issue, because if companies invest a lot of money into new technology, they probably expect a return of investment. So that return of investment can be achieved by a cheaper tooling creation or faster prototyping. Yes, that adds value, no doubt. But the big value is unlocked when we move additive manufacturing on the shop floor and we mass produce certain types. And when we then look, what are the issues to get additive manufacturing on the shop floor? We see quality control is the leading. It's 50% of all answers why additive manufacturing is not adopted yet. And that's quite big. This is significant. So it's important to talk about it. And that's my purpose today here, to guide you through how you can perform quality inspection of your additive manufacturing part, how you can scale it in a production environment, and how you can ultimately save costs by implementing a stringent quality control. And I will also talk about something else that people normally don't like to talk about. Parts can be flawed. There can be defects in the additively manufactured parts. There can be cracks or other things. So we have to look at this aspect as well. How do we perform risk mitigation? How do we ensure that our parts are safe, ultimately, when they are used in safety critical environments? So just to get started, let's have a look on the additive manufacturing value chain. And I'm pretty sure you talked a lot about the data processing, the CAD/CAM part. This is what Autodesk is all about. You talk about, or you have to deal with slicing the data to make them into a buildable job. You have to talk about post-processing, removing powder, all that kind of stuff. This is all necessary. But today it's about the quality assurance, the visual inspection, the CMM, the coordinate measurements, the metrology part, the internal non-destructive testing portion that's done with X-ray and CT. And it's a little bit challenging to tell what exactly are the relevant standards and quality requirements for additive manufacturing. Because quality control, X-ray quality control, is around for years, for decades. And there are very good standards available for casting, for plastics manufacturing. But for additive manufacturing, we don't have that yet because the technology is pretty new. And the big challenge is that we have different defect types as with traditional manufacturing. So in, for example, casting, we have very round porosities, we have pores, we have sponge porosities. We kind of know the spectrum of defects and we know the implications for the real part. With additive manufacturing, that's different, because when you have a round porosity with casting, that is one thing. But if you have, let's say, a flat porosity, because we have a layer by layer built up in additive manufacturing, the implications for cyclic loading and stress-related aspects are quite different, because a round sphere is very unlikely to act as a crack kernel. On the other hand, if you have something that has edges and corners, it can crack pretty easily under tension. So we have to reevaluate our acceptance criteria for porosities. So do we have to revise it for cracks? But most importantly, we have completely new stuff like delaminations, complete layers of unfused powders. You have never seen that in casting or other traditional manufacturing processes. So you have to figure out how to deal with that and how to make sure that your part is working as it should. So that's a big challenge. So how do we get along? And of course, what you can do in the lab is that you can take your part, you can cut it open, you can do a metallographic analysis under a microscope, and you can look at porosities, you can look at cracks, you can look at inclusions. That's all traditional. But if you do that, your part is cut. It's destructive testing. It's not doing you any good for production. You can do this with a sample, but you can't do this with every part you produce. So that's why we have computed tomography, which is then providing you a three-dimensional reconstruction of your part, which you could slice into virtual cuts, like a real cut, but just virtual. You generate a digital twin of your part, and then you perform the analysis on this, like you do here. For example, a porosity analysis. You could look for porosity distribution. You could calculate what the implications are for your part if you have such porosities. So in a very brief explanation, what does computed tomography do? You have an X-ray tube, you have a detector, you have a part, and you turn this part inside the X-ray beam. You acquire a lot of X-ray images along the way, and you reconstruct them in what you have just seen as the virtual digital twin of your part, which you can inspect. So this, for example, here is a scan of a tensile probe that has been additively manufactured, just to check before you apply cyclic loading and before you see where it actually fails. You want to calculate where it should fail to see if that works. And what you can see here is different inclusions. These are the white dots. You can see porosities, and you can see that in some areas these porosities are quite severe and will potentially affect the load capacity of that part. Another aspect that's very interesting here is this heat exchanger. So heat exchangers are the perfect target for additive manufacturing. You can manufacture crazy structures. You can have a lot of surface area that can be used to exchange the heat. You could never manufacture this design in traditional manufacturing. But of course, a heat exchanger only works if the air and the heat can actually go through the part. And what you can see here is residual stuck powder inside the part. And what we've done here is on the left side, we performed a non-destructive CT scan, and you can nicely see that it's clogged here, it's clogged in the middle. There's a lot of residual powder. After it was cut, we could see, whoops, it really is there. Of course, while cutting, it got loose and removed a little bit. So CT can help you very, very well to find this residual powder and make sure it's not inside. This becomes even more important if you apply a process caused hipping, so hyperisostatic pressing, so applying heat and pressure to harden the part and to fuse out some of the porosities inside. But if you at that point have if you have residual powder left in the part, it's of course fused to the part and stuck there and will never come out. So you probably want to find out before you heat treat the part if there's residual powder, and you would want to try to get it out before you fuse it irreversibly into the part. That's a major important analysis. And this here goes, it's a practical hint to all of you manufacturing engineers and designers out there. is that in additive manufacturing you have a non-uniform distribution of defects. Most of the time you have defects quite close to the surface, as you can see here in this area. And also this graph shows it quite well. There's a big, most of the porosities are in this area. There's a reason, because in many cases you are first lasering or sintering, at least when you use selective laser melting or sintering, you sinter the outside of the part to create a more hard shell. And then you do cross-hatching on the inside, which is done with a different beam intensity. And this creates a situation where, first of all, you have a temperature gradient before they're already sintered outside. And you have different laser intensities and temperature inputs between outside and inside. And this is creating an area between the hull and the inside, which is prone to have defects or porosity. So this is very important, especially as additively manufactured parts have a quite high surface roughness. So it's very likely that you want to surface treat it, either way mechanically or chemically. There are different ways you can do this. But by doing so, you would remove the first layers of the part. And it's very likely, at this part especially, that you open the porosities. And in many cases, small porosities are not a big deal. You can have them. They are not, these small porosities probably will not impact the part integrity. But if you then surface treat it, you have them open, it does not look nice. It might have adverse effects with lubricants and stuff like that. So you have to be very mindful on how you surface treat your parts, how thick you create this outer hull. And this is all insights that you have to already have during the manufacturing phase, which you can only get from quality control. So don't only see quality control as a tool that's applied to the ultimate product at the end of the line, but see quality control, X-ray, non-destructive testing as a tool to gain data, to optimize your manufacturing processes and designs. This is a live feedback loop we will also talk later about. And the most impressive area, I would say, is geometric deviation, because this is where additive manufacturing, for several reasons, may it be residual stress, temperature gradients, fluctuations in the laser intensity, gravity, build design. There are many reasons why the geometric deviation of a part can change from what it should be. So what you can do with computer tomography scans is that you can do actual nominal comparison. That means you compare the actual shape and geometry of the part towards the CAD and to what was intended. And what you can see here very nicely was this is joint project we did with Autodesk on, I would say this is also some kind of heat exchanger, I'd say more a showcase thing, but it really shows nicely what additive manufacturing can do. And what you see here in like purple and darker colors is negative deviations, and in brighter colors, red, is positive deviations. So the Autodesk sign here was not present in the initial sketch and drawing CAD, so it's very, very positive. There's too much material, obviously. But what's more interesting is up here, because you have a skewed part. It kind of tilts into the inside, and this can be a problem in terms of tolerances, in terms of manufacturing, but also in terms of functionality. So when we look at the cross section, you can see that on the bottom you don't have this. So you have a very nice uniform design structure, and the further you go up in the part, this is from one of the top layers, you see a big skewing in this area. Well, you see deviations in most of the part. This is classic because you build higher, so there is deviation inside the part, small ones. But significant is that on the two outside, on both sides of the outer area of that part, you see it leaning inside. And this can be compensated. So if you get that insight from your quality engineers, you could change the CAD towards a different design to compensate for that effect. And this is what you can do with a fully software driven, is that you can correct your build parameters according to the real outcome of your build. And this analysis helps you really to rapidly prototype and iterate a good part design. So again, it's that paradigm shift from using quality inspection as a tool to get new prototypes out quicker and have a better part ultimately. And of course, make sure the parts that you produce are not faulty and are safe ultimately. What you also can do with CT, it's not ending yet, is that you can perform metrology jobs. Obviously, CT systems are no CMM systems, which means you will most likely get a better resolution, accuracy, measurement, tolerance on a real calibrated perfect CMM. But you can get close enough with CT. You can get down to single-digit micron measurement resolutions. And the biggest advantage is that you can measure channels on the inside and structures on the inside. So with the CMM, yes, you can measure outside points. You can move the measuring probe towards different areas of the part. But what you cannot do is measure angles on the inside. You cannot measure distances on the inside. So this is where CT really shines, especially with additive manufacturing, because that's hands down, we are not using additive manufacturing to design simple parts that is sufficient to measure from the outside. We are using additive manufacturing to build parts that are complex and that have internal passages and lattice structures. So you would need a technology that allows you to measure that throughout the inside and outside. And a big and often overlooked area is the simulation based on actual data. I assume many of you listening in today are design engineers, mechanical designers, and you're very well aware of finite element analysis and simulations, loading or doing loading simulations, cyclic stress, breaking point analysis. That's all stuff that you probably all do frequently. And you probably do it mainly on your CAD data. So this is theoretical. But once you obtain the CT scan, where you have a real digital twin of the part with all the defects, deviations, whatever you have inside, you have a digital twin of the manufactured parts. So why not perform cyclic loading simulations, FEM simulations, stress simulations on that digital twin and actually understand what impact does the defect or the geometric deviation have? And that is a great tool to gain more insights about your part and perform a more realistic simulation. But now let's move to limitations. So you might think, wow, this is amazing, this is all nice, we have the solution for everything. Yeah, well, it's not that easy, unfortunately. So with X-ray, and I don't want to bore you with technical details, if you're interested, you can always contact me to learn more, but you have different types of X-ray tubes, from nanofocus for very high resolution to microfocus to mini focus to linear accelerators. And the more you go to the right, the more energy do these devices have, and you need energy to penetrate the parts. So if you have a very thick walls, if you have very high density parts like Inconel, steel, you need a high energy. If you have very thin and small parts with low weight or low density material like aluminum, maybe titanium, you can go with lower energy. Of course, plastics, right? This is a piece of cake for X-ray. But we have this downside between high energy and resolution. The names nano, micro, mini already name it. You are increasing the resolution as you go towards a smaller energy and a smaller focus spot. So what is important, and this is the big takeaway, you have a triangle here between resolution, speed, and penetration. You can't have it everywhere. If you want high resolution, you cannot scan big parts. If you want high resolution, you cannot scan parts fast. If you want to scan big parts, forget about speed, forget about resolution. And you have to, your quality engineers are moving in that spectrum. And I will come back to this later, why this is so important to keep this in mind. CT, quality inspection, is not a miracle tool. It has physical limitations, and you have to keep them into account to design parts that actually are inspectable by your colleagues. And One last hint, it's again a bit technical, is that X-ray is a cone beam technology, which means to achieve more resolution, right, you have to magnify. That means you have to move the part closer to your X-ray tube. If you do this, at the same time your field of view is reduced. Typical detectors that are used for computer tomographies are 40 by 40 centimeters, right? And if you have a magnification of close to 1, so you're very close to the detector, you can X-ray a part, or you can scan a part of 40 by 40 centimeters. But you are limited to the resolution of the detector, let's say 100 micron. So your defect detectability is somewhere between 200 and 300 micron. If you want to achieve a defect detectability of 30 micron, you need to have a scan resolution of roughly 10 micron to safely detect the defects. And that means you have to magnify by factor 10, which limits your active area to 4 by 4 centimeters, which means the part that you scan is absolutely tiny. And this is what you have to keep in mind. When you define your defect detectability criteria and your quality inspection criteria, keep in mind if it's very high, then your scan part can be very, very low only. And this might be an issue. So there is a trade-off and it has to be addressed early. And this is bringing me I'm saying this with a blinking eye. It's a very classical example that design engineers, don't take this offensive please, get very excited about additive manufacturing and think about all these things they can do, bionic designs, more weight reductions. It sounds great as a marketing message. We can save 40% in weight, but please keep in mind, if those last 3% on that part led to a situation where it's not inspectable anymore, it will probably not get qualified. And if it doesn't get qualified, it will not get produced, and it will not be used for anything else than a nice marketing showcase on an exhibition. So what's important is to talk early to your colleagues in quality and to ask them about the limitations of the technology being used. Maybe even tell them about what you learned today about computer tomography, about how we could solve certain challenges, and then make sure to design not only for manufacturing. This, luckily, is something that's done a lot, right? It's not only designed for functionality, that is clear, but it's also been designed for manufacturing, especially in additive manufacturing. You build in support structures, you build in certain design principles, that's clear. But what you also have to keep in mind, the limitations of your quality inspection processes. So you have to design for inspectability. And this is what I'm coming here today to ask you. Don't go all the way what you can do with the technology if it leads to adverse effects and problems down the road with post processes like inspection. Talk early and make sure that what you design can also be qualified. So long story short, here's the summary, is computer tomography is probably the only reliable inspection technology for additive manufactured parts. This is also being stated by leading qualification bodies like ASME or ASTM. There's a lot of work being done on standardization and quality standards, but there is really a big but. Standardization is not yet finalized, and it will probably also take a couple of more years to be the case. And until then, we will only see parts in small areas like a door hinge or a seat bracket, which is not giving our companies the savings that are promised by additively manufactured parts. In order to unlock these savings, we have to think early about how we productionalize it, how do we make sure we can produce it in a bigger quantity and we can make them safe and qualified, and we can also manufacture safety critical parts. And unfortunately, there's a big fundamental gap between what engineering and design wants and what the technology can deliver. This is sometimes the case in additive manufacturing technologies, but this is also the case especially in inspection. And there needs to be a bigger, a more close discussion between quality professionals and design engineers. But unfortunately also on the non-destructive testing side and quality side, there is a skills gap. Computer tomography is a highly complex technology. Most NDT engineers are used to X-ray that are applied for 2D inspections for casting parts. They are used to ultrasonics, they are used to penetrant inspection, for surface and crack inspection. But CT is a rather new technology, and there is still a lot of knowledge to be built. And this is also where I would suggest start early, have it in the lab, use it for design iterations, use it for optimizations before you move it to the production line. It is a step to take. And the unclear quality thresholds, this is something that has to be worked out. And we are working on this with a couple of our research partners on how much tolerance do we actually have in additively manufactured parts? When do they fail? There's a lot of research going on, and it's giving us insights to build in the right tolerances into the parts. And the big risk is that additive manufacturing currently is suffering in the eyes of top management because a business case was promised: savings, material savings, time savings, weight savings. And yes, on the prototype level, they are manifested. You can see them; they are tangible. But until these promises are really delivered, this is only the case once they are also in the production and really save the costs. So last but not least, I want to point out a white paper that we've done on surface treatment and the combined usage of surface treatment and CT, and how what is preferred, first surface treatment, then CT, the other way around. It's a really, really interesting read. And if you're interested, please feel free to scan that barcode, type in your information, and you will receive it. Otherwise, please feel free to contact me at any time if you want to learn more about it. I try to keep it concise and high level for you to give you a bird's eye perspective on what to take into account with additive manufactured parts and quality control. I hope it was worth your time, and I wish you a great day on the Autodesk Automotive Forum. Thanks for your attention.